Okay, so let's see how you would use those previous formulas and properties to evaluate a summation, a more complicated one. So the idea is basically this. We have to break this apart enough to get just really things that we have the summation formulas for. So sum of a constant, sum of I squared, sum of I cubed. All right, so what I'm going to do here is notice that n squared is really a constant, right? It's not changing. It's set. It's fixed to some value. We don't know the value right now, but it's fixed. I is the only thing that's constant. So that means the n squared can come out. I can say 1 over n squared sum I equals 1 to n of 2i plus 1. Okay. And then the next thing is I can see that I have the sum of two different types of terms, so I can break that up. So 1 over n squared times the sum I equals 1 to n of 2i plus the sum I equals 1 to n of 1. All right. And then even within this one, I can take out a 2. So now I have 1 over n squared times 2, the sum I equals 1 to n of I, plus the sum I equals 1 to n of 1. All right, so now I'm in a good place here, because if you notice, what I have is I have two summations that fit my formulas, the sum of I and the sum of a constant, in this case 1. So I would have 1 over n squared, 2. So now what should this sum of I be? Well, that was just the one from the story. Summing 1 to n of I should just give us n times n plus 1 over 2. And then summing on this one, summing 1, that's summing a constant. That should really just be 1 times n, c times n. All right, summations are now gone. We were able to use those formulas to get rid of the summations. Okay, so let's just clean this up. 1 over n squared times n times n plus 1 plus n. Okay, so then we get, so if we wanted to do this, that inside would really be n squared plus n, or n squared plus 2n over n squared. Factor out an n, and we lose 1 from there, and so we get n plus 2 over n. And there you go. If you wanted to calculate what this summation is for any n, it's just n plus 2 over n. Okay. Now often we don't want to know what some specific sum is, but we actually want to know what it is when n goes to infinity. So this is something we might want to look at. So just leave that n goes to infinity on the outside while we deal with the rest of this. Okay, so again, I can pull out, actually I can pull out not just 1 over n squared, I can pull out 16 over n squared as constants. So then I'm going to have the sum I equals 1 to n of I. Okay, so I have the limit as n goes to infinity, 16 over n squared. Let me put brackets to make sure we see what we're doing here. And then again, this summation here, that's our summation that we know from the formula. That would just be n times n plus 1 over 2. So what do we get here? All right, we get the limit as n goes to infinity. We would get 8 from the 16 over 2 times, well, one of the n's would cancel, so we get n plus 1 over n. Well, this is a pretty easy limit to do. The limit of 8 is 8, and the limit of n plus 1 over n, that's just a polynomial over polynomial where they lead with the same, n plus 1 over n, you just have a polynomial with the same power on top and bottom, so we go to our coefficients as 1 over 1, so the limit there as n goes to infinity is just 1, and we get 8. So interestingly enough, this whole term, this whole expression in the limit as n goes to infinity is 8. And that's how we can often use this in a very useful way. In fact, we can bring this back to our area calculations. So we're going to use the sigma notation and get our previous formulas for the area. All right, so let's say we're looking at f of x over ab divided into n subintervals, as shown in this picture here, where they each have a width of delta x. All right, so the right endpoint, so the area using the right endpoint would be the sum I equals 1 to n, the n rectangles, where now we're going to do a height times a base, just like before. The base is still just this delta x. The height depends on the point we're using. So this is just general right now. We're saying CI. We haven't applied the right endpoint. But look at what a right endpoint is. All right, so let's say, let me come over here. Let's say you're starting at A. That would be your first value. Then you have these intervals here. Take the first interval. The right endpoint is here. But if that's delta x width, then to get from A to that first right endpoint, you would have to add a delta x. In other words, 1 delta x. To get to the next one, you would need another delta x, you'd need a total of 2 delta x's. In general, to get to, say, this point here, that would be a plus I delta x, where I is however many, whatever interval you're on. So this is a way of writing CI for the right endpoint. A plus I delta x. So if I'm using the right endpoint, then I'm going to be evaluating the function f at this right endpoint to get my height and multiply that by my width. I'm going to do that for every rectangle and add up the areas for the n rectangles. That's turns out to be the cleanest formula. The left endpoint is actually a little messier. It's the same format given here, but this is what CI looks like. In other words, if you want to stay at A for I equals 1, you would have to add 0 delta x's, which means you'd have to do I minus 1 times it. So that is the formula for the left endpoint, and even messier is the midpoint, which your CI comes out to be like this. So we're going to see that we can do a lot with just the right endpoint, and that's our commonly used one because, well, little hint ahead, it's not going to matter which one of those we use. So we're going to use the cleanest one, the right endpoint version.